I want to consider the simplest model of a production line with 8 workstations and one machine at every workstation, and assume that that machine is operational, and assume that here the workstations, 8 workstations with one resource here at every workstation, and the resource is operational, and assume that we implement some kind of pull with the inventory limits as shown in this column, and assume that the cycle time is exactly 10 minutes at every workstation, and resources. Let us assume that each one has a standard speed. If you want to consider higher speeds, you can assign like 1.2, 1.3, it means 20% more, and assume that all resources are available right away, and no failures, no repairs, no calendars. This is the simplest balanced production line with no random variation in cycle times, no uncertainty. And I'm going to simulate now. Before I simulate, I want to show you, animation for a few minutes. So let me simulate this. This is the animation. So it is a crude animation, and but still it is valid. It is scientific, but it's not so impressive. Let me skip now this animation because it will take a lot of time to simulate the production of 100 pieces with animation. So I'm going to skip it now. So this is the output. I can remove others. So this is the current one. And the production line takes 1070 minutes to complete all 100 pieces, and it produces one piece for every 10 minutes. On the average, you would find 7.48 items on the line, and the average lead time on production line for every piece is 80 minutes. So let me show you the flow of these pieces on the line. So every piece flows through these 8 workstations without waiting anywhere. There is no in-process waiting because it's a balanced line with no random variation, no uncertainty. Everything is perfect. So therefore, every piece is flowing without waiting anywhere. It's a perfect one-piece flow. And you can also see that in other chart. Here you see the workloads for resources. R1 to R8. R1 is processing these pieces in this order, R2 also in the same order, likewise. So now let me bring a small change in this system. For example, there is a problem initially at a 4th workstation, and the first piece will wait for 30 minutes. And here, now you see here, the third, this first piece is waiting for 30 minutes because R4 is not immediately available. And every machine can process only one piece at a time. And these pieces, they go through a sequence. For that reason, every piece waits for the same amount of time, the 30 minutes. And now the make span increased from 1070 to 1100. It increased by 30 minutes, the same amount, like the initial waiting time. So how can we recover this loss of time? The only way you could recover this loss of time in completing all the workload is by increasing the speeds of these machines R4 to R8. So let me go and increase the speeds. For example, I would increase by 10%, the speeds of these machines. I have to increase for all of them so that they can catch up the initial machines. Now I'm going to run the simulation again with increased speeds for those. And now if you look at this one here, because they are working faster, the machines from R4 to R8 are working faster. So that's why the waiting time is gradually decreasing. And if you scroll down, you would see that after some time, these pieces do not wait anymore. For example, from piece 34 onwards, they don't wait for resources at all, no waiting at all. It means if we increase the speeds of R4 to R8 up to for first 36 minutes, then you could recover the loss of time. That's why you can also see in the full view. So only initial time during the first 360 minutes, the pieces are waiting at fourth workstation. After that, they go smoothly. So let me consider another scenario. Let me this is a starting point. Now I would introduce calendars. Let us consider the production line with calendars for resources. So I'm considering a simple calendar in which the resource will be available for 80 minutes, unavailable for 20 minutes, and the cycle is repeated. The same calendar is assigned to all of them here to keep it simple. So I'm going to simulate this production line of 8 workstations with this calendar now. But again, the cycle time is exactly 10 minutes per every piece at every workstation. So now, because of the calendars, the line is producing one piece for every 12.63 minutes instead of 10 minutes. And the make span, the total time needed to complete all 100 pieces is 1330 minutes instead of 1070 minutes. So now, let me bring the same change here again here. For example, here what you see, this yellow color is the waiting time of the pieces, because during this time, the resources are not available as per the calendar. So let us assume that initially, there is some waiting at the fourth workstation. So therefore, let's say take the same time, the 30 minutes, for example, here. So for 30 minutes, the first piece is waiting, therefore other pieces are also waiting. So these are the waiting times because of the delay, and these waiting times because of that calendar. So now the make span increases from 1330 to 1360. That is 30 minutes extra. That's because of initial delay of 30 minutes. How can we recover in this case? So another, instead of changing the speeds, you could do another way. For example, I will make these resources available for 5 more minutes. That is 85 minutes available in the cycle and unavailable for only 15 minutes. So let me assign the same calendar for all other resources. It's 15. So what I did, I assigned a different calendar for resource R4 to R8 because of the delay, and I increased the available time in the cycle by 5 minutes and reduced the unavailable time by 5 minutes. So let me run the simulation with this change. Now you could see that this 1330 initially, the make span, now it's slightly less than it because we increased the speeds. The available times, in the calendar. And if you look at here also, you would see the same, after some time. So let me see here. So if you take 600, for example, if you take from this P47 onwards, the pieces do not wait at fourth work center anymore. So it means for up to the first 20 minutes, if you assign that calendar, 85-15 calendar, then you could recover the loss of time. So these are ones. That's the next scenario. I would consider one more scenario in which I remove the calendars, but I would assign different speeds. Now what I will do, I will assign different speeds. So this is 1.7, then this is 1.6, and 1.5, 1.4, and 1.3, 1.2, and 1.1. What I'm doing basically, I decreasing the speeds. This is the fastest one. The next fastest machine is this, likewise. But this is a normal one. It works at a standard speed. So this is the bottleneck in this case, because the cycle time is same. The last one is the bottleneck. So now let me simulate this scenario. So I still, I'm considering this a balanced line. No, it's not anymore balanced because the cycle time is same, but the speeds are different. So let me simulate this scenario. So let me show the Gantt chart. Where the first one is the fastest one. The second one is slightly slower than the first one. Therefore, the pieces are waiting before the second workstation. Similarly, because of the difference in the speeds between second and third, the pieces are again waiting there. This is what's happening. So as the time goes by, the waiting times increase, but it will not increase to infinite because we put a limit, inventory limit 5, because the inventory limit is 5 at every workstation. So therefore, every piece waits for only certain amount of time. So that you see here. So if you can take a full view. So from here onwards, if the system is stable, the pieces are flowing through the system in this fashion. The first operation is done during this time, second operation during this time, because they're waiting for a while because of the differences in the speeds. So basically what you're saying, what will happen if machines have different speeds, even if the cycle time is same. That is what I have shown you. And if you look at this here, uh, basically it's some machines. I'm seeing the resource view. You could see after a while, the faster machines will be waiting for pieces. The yellow segment shows the waiting time of the resources. So because they're faster, they're waiting for longer time. So I would consider one. I'm just showing you different scenarios. You could consider any scenario involving these 7 factors. Yeah, these 7 factors. I consider simulation of material flow on production line with respect to only these 7 factors. So this is the limitation of my simulation. I'm not considering, the rejections, rework, and all right now. Okay, you could consider any model involving these 7 factors, but I'm showing you some of them now. So what I will do now, I will go back to the normal case. But I will not I will have multiple parallel machines at every workstation. So right now I'm assuming that there are 4 parallel machines at every workstation. All 4 are activated. All 4 are operational, and the WIP limits 5 at every workstation, and cycle time is exactly 10 minutes everywhere. I'm going to simulate this multi-resource scenario for 100 pieces. So now let me simulate now. You could see now when there are 4 machines at every workstation, the system gives 1 piece for every 2.4 minutes instead of 10 minutes. And we complete all 100 pieces in 320 minutes because of 4 machines. Otherwise, it would have taken 1070 minutes. Okay, now let me show the flow of pieces graphically. You can see the first 4 pieces. There are 4 machines everywhere, so their first 4 pieces are going, in this fashion, like a one-piece flow. Every piece is flowing through the system without waiting anywhere. Here again, still is a balanced one with multiple machines. Now I will make a small change. Suppose at the third workstation, only 3 machines are operational because of a problem with the fourth one, and assume that only 2 machines are operational. So I want to run this simulation. So could you guess how the material will flow? It's not easy to guess, how the material will flow. I'm going to show you. But again, we implement every workstation is 5. We are implementing a pull. So let me simulate this scenario. So let me show the Gantt chart. So here these 4 machines are initially running at first workstation, second workstation. There are only 3 are available at third one. Because of that, P4 is waiting. So as the time goes by, you could see that after a while, the line is using only 2 machines everywhere. This is because The sixth workstation has only two machines, and we are controlling the whip at every workstation. Because of those two reasons, only two machines are used finally at every workstation, and this is how the pieces will wait. This is the flow of pieces. So you can also see the same thing in terms of workloads and machines in this fashion. But you can also see the resource utilizations here in this one. This is a multi-machine scenario. Now let me consider another one is so far I'm considering the balanced line with no variation. I would go to the case where let me restore one machine case. So I'm back to normal. So I would introduce random variation now. I would consider assume that the cycle times follows normal distribution with the mean 10 and standard deviation 2. I'm going to simulate the production with cycle times following normal distribution. So let me simulate now. I created 100 jobs now for this scenario. I'm going to simulate now. So see what happens now. Because of the variation, the only thing is instead of fixed cycle time, we are assuming a normal distribution. Because of that, the system is producing one piece for every 10.84 minutes instead of 10. And the make span now is 1147 instead of 1070. And let me show the flow. How the pieces flow because of the way random variation in cycle times, the pieces will be waiting like this. And I can show the full view. So you can see the flow of every piece in the chart. Similarly, you can see the resource chart. I'm showing you whatever model you take, you can see the flow of the pieces through the trace of simulation. But you can also look at the animation to understand the material flow. But you won't grasp fully, the flow of them when you look at it in real time. But if you take the trace of the simulation and put it in the chart, then you can take your own time to understand how the material flowed. That's the main advantage, of this, compared to the animation. Normally, simulation, viewed as animation. So animation, observing the animation of simulation gives some knowledge, no doubt, but you don't have much time to think because the animation is running, right? But if you capture the trace of the simulation and put it in the chart, the Gantt chart, then you have ample time to understand how the material flowed through the system, where the bottlenecks are, when they will occur, all that can be studied in a systematic fashion. So that is the reason I'm presenting this trace of simulation in the charts for a better understanding. Okay, now I will what I will do, I will take the again deterministic case, but unbalanced scenario. I'm considering different scenarios now. So let me, for example, the cycle time is 24. Here only 7. There is a 32, and say 15 here, and 36 cycle time, pretty large, and 10. And because the 24 is pretty high, I will put two machines here um, to reduce the unbalancedness. Two machines here and three machines here. And, now, even then, here the effective cycle time is 12 because there are two machines. Effective cycle time is 16 because of two machines. Effective cycle time is 12 because of three machines. However, that fourth workstation is a bottleneck because the effective cycle time is 16. So let me simulate this unbalanced, production line now. So let me look at the resources. Here, there's a normal one. So I'm going to simulate now. So here, you remember that the fourth workstation, the effective cycle time is 16. That is the reason you get here the production of every piece for 16 minutes. And let us see the flow. This is the flow of pieces on the production line. So you could see that because the two machines are there at second workstation, as you see here, two machines, second one, and the fourth one, and the seventh one, three. Because of that, you see the two machines running simultaneously. And here, the fourth workstation, two machines are running simultaneously. And at the seventh workstation, three machines running simultaneously. This is how the pieces will flow through the system. There's a lot of waiting time, so we allowed the waiting of up to five pieces. That's why you see the maximum of five pieces waiting before any workstation. And so what I will do now. So how can we, if everything is deterministic, can we release these pieces at the first workstation such that you get one piece flow? So in this unbalanced case, with different machines, different count of machines at the workstations, how can we achieve one piece flow? That's what I want to show you. So let me go to this one. Here I will run another algorithm and go back to this and simulate now. So now let me show 1 second. Did I do that? No, I had to run this one. So now see, the makes mine did not change, but I think I didn't run it. 1 second. Okay, now here, let me show the flow first. Here you see, when I run a different algorithm, it releases the pieces to the first workstation at the right time. Uh, you know, but it doesn't keep the first one busy all the time. But every piece flows through the system without any waiting at all. Though the cycle times are different, the number of machines varies with the work center, but still we can release every piece at the right time so that you achieve one piece flow. I wanted to show you. Now, I will consider, let me see the scenario. So the material flow, one statistical variation I have shown you. I wanted to show you what is the interaction between inventory limits and statistical variation. I forgot to show you. What I will do, I go to this the balanced line with normal distribution sigma 2 and one machine everywhere. What I will do, I will run four scenarios, of this one. One is with WIP limit 5 at every workstation, with the sigma 2 at every workstation, I will run one scenario. In the second scenario, I will reduce the standard deviation from 2 to 1. In the third scenario, I will reduce this WIP limit to 2 and run with the standard deviation 2. And fourth one, with WIP limit 2, I will run standard. All these four combinations I'm going to run now. So for the first combination, WIP limit 2 and standard deviation 1. So let me run it now. I'm simulating. Let me remove all of them. So this is the one. The four scenarios. This is the first scenario where the WIP limit is 5 and the standard deviation is 2. And let me go and reduce it to 1. Now the standard deviation 1, I create job information accordingly and simulate. Now what happened, when I reduced the standard deviation from 2 to 1, then I increased production from 124 to 131. Right, it increased. Now, so now let me take in the other two scenarios. So let me take it as it is a WIP limit 2 and standard deviation 2 and create the jobs and simulate. Now this scenario, the WIP limit is 2, standard deviation is 2. We got this. And fourth one here, 1, assign 1 and create jobs and simulate. So 4 scenarios I got. Here, the bottom one, WIP limit 5, sigma 2. And with the next one, WIP limit 5, sigma 1, you got this. But here, WIP limit, so WIP limit 2, so you can so understand, so the interaction between when WIP limit, what I wanted to show you basically, when at a higher WIP limits, the advantage of reducing variation is not much. But when the WIP limit is low, the effect of changing that variation is more prominent. That's what I wanted to show you. So you can see here, the, but in this case, I tell you, because I'm running only 10 pieces, sorry, 100 pieces, you don't see that. To demonstrate that, I need to run, and I will repeat this exercise if you don't mind. Let me start with the 5 and make it 2 here. I'm running this because I have to run for not for 100 pieces, I have to run for 5,000 pieces. Then only, the line becomes stable. So I'm going to run now with this scenario. But I simulate for 5,000 pieces with WIP limit 5 and standard deviation 2. And so instead here, let me make it 5,000. So it may take so now I will run it for 5,000 pieces. So it may take about 10 to 15, maybe 13 seconds it may take, because I'm simulating for 5,000 pieces with a random variation cycle times. So I got this one now, that for 5,000 pieces, WIP limited to 5 and sigma 2, the average daily production is 141. So let me remove other previous exercises. Let us start with this. Here the WIP limit is 5, standard deviation is 2, the average daily production is 141. So I go to the another scenario. This 1, standard deviation 1, I reduce it and recreate the jobs accordingly and simulate again. So it may take again about 15 seconds to run this simulation. So let us see the difference, the advantage of reducing the variation from sigma 2 to sigma 1. Here, it is not much. So basically, with WIP limit 5 at every workstation, if I improve the variation from sigma 2 to sigma 1, a standard deviation from 2 to 1, really I didn't gain much. I did not gain much by cutting down the variation when the WIP limit is high. So let us see the other scenario. WIP limit is low, only 2, and set sigma is 2, right? Okay. So now, once again, I think I didn't, yeah. So I'm considering this is a third scenario with the way, here, because the WIP limit is low, you're losing some productivity. That's not sufficient. But let me run this case. Let me reduce that sigma to 1 and run it again. This is the fourth experiment. So I'm showing you 4 experiments. 2 experiments with the WIP limit 5, 2 experiments with the WIP limit 2. So here, when the WIP limit is 2, improving the variation from sigma equal to 2 to sigma equal to 1, I got this much advantage. But at a higher WIP limit, improving the variation, only this much, almost nothing. So this is what I wanted to show you. These things, mostly we talk, by common sense, these effects, but the advantage of simulation is you can be more confident, of these concepts. So always the system is affected by the seven factors, but there is interaction among them. Those interactions are not known. You know, there's no method in lean manufacturing to understand the interaction effects of these factors. So in the lean manufacturing, there's only one principle: improve, 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 improve. Without really understanding, the behavior or the effects of these factors on productivity or the KPIs of the system. So that's the reason I feel this the Monte Carlo simulations, you know, they serve as a complementary role in lean manufacturing. Okay, now I demonstrated to you, the interaction between the inventory limit and the variation. So I will consider finally one case, an unbalanced one with the failures. So let me consider, assume that this takes 7 minutes, this takes 9, this takes 12, and again this takes 12, and 7, 9, 8. So this is an unbalanced line, and assume that there is no randomness. And let us take this WIP limit 5 at every workstation. And I would introduce some failures for some machines. For example, the second one, the failure rate is 0.01. It means on the average, for every 100 minutes, the machine will fail. And assume that there's a fixed repair time, say 25. And similarly, let us assume that the machine at the fourth workstation also has the same failure rate. For every on the average for every 100 minutes it fails. And let us take here also. So I'm assuming that three machines have failures, repairs and failures, and there is no cycle time variation. So let us simulate this scenario. So I need to simulate for 5,000 pieces to be accurate. So I create the jobs. So now I'm going to simulate this case and see what happens. So I'm simulating a production line, an unbalanced production line with no random variation cycle times, but machine failures. And here, because of the machine failures, the system is producing at 12. Though, apparently these are the bottlenecks, 12 minutes, but, it is producing one piece for every 13 minutes. And the average daily production rate is 100, almost 111. So now, if you look at, the resource utilizations, so here you see the input and output for every scenario, in this chart, in this window. So what we considered, the machine failures for the failures for three machines, so the R2, R4, and R6, and these are the cycle times and no random variation. And here the utilizations in the simulation, you could see the utilization of these machines. The third machine and fifth machine are the bottlenecks. Apparently, the utilization is very high compared to that. So therefore, normally what we try to do, we want to bring some improvement. So because they're pretty busy, what I want to do, I want to reduce the cycle times there. What I will do, I will try this one, because cycle time I will reduce by 20%. I reduce 12 to 10. It means I'm reducing the cycle time by 20% and try. And let me create the jobs accordingly. So now what I did, because the third machine is a bottleneck, very busy, I reduced the cycle times some effort by 20%. And I want to see the effect, the advantage. So the advantage is how much I save. The daily production rate increases from 112 to 113. only. I'm not happy. So now what I will do, because now let us look at the this scenario. This is the apparently very busy, the fifth work station. So therefore, I want to reduce this also by 20%. So I make it 10. So what I am doing, even the fifth workstation, with some effort, I am reducing the cycle time by 20%. That is 12 to 10. So let me create the jobs accordingly and simulate again. So now what I did, because those two machines are pretty busy, I reduce the cycle times. Now, what I did finally, from 111 to 114, only 3 paces. So therefore, I'm not really seeing much gain by reducing the cycle time by 20% at these places. That should surprise me, right? Because if you look at that, this scenario here, initially these two, with cycle times 12, these two are pretty busy. So therefore, I focused on on improving at those workstations. So I worked hard and reduced the cycle time from 12 to 10 at those two workstations. But the advantage is not there. Now, what I will do, I will restore them. Hmm? I will restore that to 12. Instead, what I will do, I reduce this repair time to 10. From 25 to 10, and I would simulate. Now let me create the jobs again and simulate. And I want to see the effect of reducing the repair time from 25 minutes to 10 minutes at that, that fourth workstation. So now I improved from 111 to almost 116. So that is substantial, compared to the drastic reduction at the workstation. But this is not visible. When you look at that, when you look at this experiment here, you don't find that they're not improving, making some improvement in the repair time at fourth workstation will bring substantial improvement. It's not easy for you to guess. So by doing this kind of experiments, one can bring out the hidden, improvement opportunities. This is basically what I want to show you. So basically, I want to present a simple, a scientific, simple tool which engineers and managers can run without any simulation knowledge. Just put these numbers, and see how the material will flow. And you can do some experiments on that to see the effects of changes in those 7 factors. So therefore, it gives a better understanding of the effects of these factors. So in lean manufacturing, you are very practical. You want to improve everywhere. Wherever possible, you want to improve without having a comprehensive knowledge of the effects of these factors. So therefore, the Monte Carlo simulation of material flow complements what you do in lean manufacturing. So therefore, this is a complementary one, I would say. Even factory physics plays a complementary role. And I would say this is a more flexible and versatile than the theoretical factory physics. So if you have any questions, and let me know. Basically, I want to conclude this one saying that the Monte Carlo, a simple, quick, easy Monte Carlo simulation of material flow and production lines will complement what you do in terms of lean manufacturing. So it gives a comprehensive knowledge of the dynamic nature of production lines. You could see the effects, how various factors affect, the KPIs of the production line. This is what I wanted to show. So the simulation exercise should be simple, quick, and easy. Then only the people in industries they can run simulations. So that is the reason I developed this FlowshopSim. This is not to make big money out of that, mainly to promote Monte Carlo simulations in factories. So if you want to run the Monte Carlo simulation for multiple scenarios, yeah, because this is basically an academic tool. So I'm providing only 50. I'm considering only 15 different products in this academic tool. So you could create, you could consider production of up to 15 products, and simulate them. For that purpose, you have to use this window. Here, you can also determine the sequence of products, by specifying this in these rows. You could go, that can be repeated. You can have in 100 orders. Here right now, 15 orders for 15 products, but you can have 100 orders. But for every order corresponds to one of these, 15 routings. So you could also specify the quantities, how much. The only thing is the changeover times right now, they are not implemented. So when you move from one product to another product, there may be changeover time that is not yet completed. There, that is still June. Other than that, we can run. I can simulate now. For example, the first, let me consider this for example, only four of them. And so suppose this, but these are somewhat similar. So this takes 20 pieces. This takes, so say 20 pieces, and this takes some 10. And now, before doing that, I go to the routing one here, and I'll say only this takes 5 minutes, 5 minutes, so that you could see easily on the Gantt chart the runs. For example, this takes 2 minutes everywhere. So I'm considering that the production of these four types of products. So let me simulate now, create jobs now, and jobs are created, and run the simulation and look at the Gantt chart. Now you can see that one, the first five pieces have one routing information, and the second one here only five. The cycle time is 5 for everything, so that's why you see five. These 20 pieces. The next 10 after that 10 pieces. These are the 10 pieces. They have different routing information, and the last 20 have a different one. So what I mean, you can simulate the production of multiple products. This is what I demonstrated. Right now, the changeover time is not considered, which I'm going to include later. All right. So any other questions?